So let us begin with lecture 2 of electromagnetic induction. So in this lecture we are going to deal about motional electromotive force or motional EMF, motional electromotive force, or it is regarded as motional EMF. We also regard it as motional EMF. So when a conductor moves in a magnetic field, then the charges inside the conductor experiences the magnetic force. So what do I basically mean to say is that if we consider that a magnetic field is present in the region like this, directed into the plane of paper, having magnitude B. So we are considering this is the value of magnetic field B that is directed into the plane of paper. We are writing the magnetic field strength as B. Now if we place a conductor, so if we place a conductor like this, having a length L, and if we consider that this conductor is moving with a velocity v, so now if we consider the direction of v cross b, why we are considering the direction of v cross b? It is because when the conductor is moving in a magnetic field and the charges inside the conductor will experience a force that is given by F vector is equal to q v cross b. So the positive charges inside the conductor will start accumulating on the upper end because the direction of v cross b is on the upper end of the conductor, while the free electrons will start accumulating on the lower end of the conductor. So we say that due to this charge accumulation at the two ends of the conductor, an EMF is induced which is regarded as the motional EMF. Now in equilibrium, the electric field force will balance the force of the magnetic field, and we can say that due to this induced charges, the electric field induced will produce an electric field which will produce a force on this charge. So just like the magnetic force is written as Fm, which is equal to q v cross b, and electric force will also act on this charge which is equal to q e vector, and then we can say that if this force balances each other out in equilibrium, that is the sum of the magnetic force and the sum of the electric force will become 0. So in that case we can write it as q v cross b plus qe is equal to 0, or we can write from here that E vector is equal to minus v cross b. So we get an expression like this from here, that E vector is equal to minus v cross b. So if we wish to write the potential difference developed across the ends of the conductor, so if I write the potential difference that is developed across the ends of the conductor, then we can write from this equation that Vb minus Va is equal to negative integral of E dot dl from A to B, and hence we can modify this equation to look in this way, that Vb minus Va is equal to V cross B into dl. So it will come out to be V cross B dot dl, and the limit remains A to B. So for this, for a conductor of length L, for a conductor of length L, I can say that the potential difference across the end will be BLV. So the value of potential difference across the end of the conductor will turn out to be BLV, and this is regarded as the motional EMF. So over here we write if the circuit is incomplete, if the circuit is incomplete, then the terminal potential difference then the terminal potential difference can be written as E, which is equal to integral A to B V cross B dot dl. V cross B dot dl. Or we can also write that E is equal to integral A to B dot dl cross V. So from the equations which we have written, it can be said in this way, that as dl cross V is the area swept per unit time by the length dl vector, as dl cross V is the area swept per unit time by the length dl vector, and hence I can say that B dot dl cross V, so B dot dl cross V, that is this term, is the flux of the induction through the area. It can be regarded as the flux of the induction through this area, and we can say that the motional EMF can be written in this three equations. Over here we have already written the two equations, so we can write it in the form of three equations. That is, E can be written as from A to B V cross B dot dl, or we can write it as B cross dl dot V, or we can also write it as dl cross V dot B. So all these three equations are possible for the motional EMF of the conductor, and we will end up getting the magnitude of EMF induced across the end of the conductor as BLV, and hence it is important that V, B and DL, if any two of this, that is V, B and DL, become parallel or anti-parallel to each other, then the value of EMF induced will become 0. Or we can say that V, B and DL must be mutually perpendicular to each other for us to apply this equation of EMF induced, or the motional EMF induced, where we say that potential difference is equal to BLV. So if I draw one more circuit analysis for this particular case, so I can consider it in this way, that if we are considering that a conductor is moved in a region of magnetic field B having a length L and velocity V. So if we consider that this is the conductor, so over here I am drawing so I am considering over here something like this. So this is a conducting rail on which our conductor will slide with a velocity V, and at the end of the conducting rail I am fixing a resistance R, and over here we are considering that a conductor is placed which will move with a speed V. So it will move with a speed V, and the length of the conductor is marked as L. So if it is moving with a speed V, and if we have calculated that the potential difference or the EMF induced is equal to BLV, so we draw it in this way, that if I draw an equivalent circuit for this particular question, so I can consider that this is going to be the EMF induced, which is equal to BLV, which is connected across a resistance R. which is connected across the resistance R. So now we can determine the positive terminal either by the direction of V cross B. So if we determine the direction of V cross B, then we are finding that the upward terminal over here must acquire the positive charges, and hence we are saying that the positive terminal must be in this direction. So either we can do it in this particular way, or the other possibility is that we can apply Fleming's rule for this particular problem. So over here we are relying much on V cross B. So if we determine the direction of V cross B, then we can replace it with a battery of EMF BLV. So just see the direction of V cross B. So the V cross B for this particular problem is pointing in the upward direction. So we say that the upward terminal is going to behave like a positive terminal, and the lower one will behave like a negative terminal, and we can draw it as a battery like this. And now if we calculate the direction of current and the magnitude of current, then the value of current in this particular resistance can be written as I is equal to BLV upon R. Now if I consider that this particular rod which we are considering is having a resistance small r. Suppose it is offering an internal resistance, offering a resistance small r, then I will replace this same circuit in this fashion. The battery polarity will remain the same, and the resistance associated with this particular conductor will be drawn like this. So we are writing it as small r. The value of EMF is equal to BLV, and this is capital R. And this time if we calculate the value of current I, that is current induced, then the value of current induced can be written as BLV upon R plus R, where small r is the resistance offered by the conductor which is moved in the magnetic field. So it is very important that to keep these things in mind, that the value of B, L and V are mutually perpendicular to each other. If any two of V vector, B vector or DL vector become parallel or anti-parallel to each other, then the EMF will become zero. Then the value of EMF will become zero, and the direction of the polarity we have determined over here by finding out the direction of V cross B. So if we determine the direction of V cross B, then you can write it as BLV on the upper terminal, or the other possibility is applying Fleming's right hand rule. So if you apply Fleming's right hand rule, then we can say that the index finger will point in the direction of magnetic field, your thumb will point in the direction of velocity, and your middle finger will point us in the direction of the current. So we can do that as well in this particular problem. So in this case, the middle finger is pointing in the upward direction for the conductor of length L. So I can say that the upward terminal will behave like a positive terminal. So we can use Fleming's right hand rule for the determination of the polarity of BLV, or we can take the direction of V cross B as the direction of the positive terminal, and can draw an equivalent circuit diagram for this particular case. Now in the another aspect over here, we are considering a rotating straight conductor in a magnetic field. EMF, motional EMF due to a rotating conductor, motional EMF due to a straight rotating conductor. So we are again considering that a region of uniform magnetic field is present, in which the magnetic field is directed into the plane of paper, having magnetic field strength B, and a conductor is rotated with an angular velocity omega in this region of magnetic field B. So in this region of magnetic field B, we are considering that a conductor is rotated So we are considering that a conductor is rotated with an angular velocity omega. The length of the conductor is equal to L. The length of the conductor is equal to L. So if it is rotating with omega, so at a distance x from the hinged point, at a distance x from the hinged point, I am selecting a small patch. I am selecting a small patch of thickness dx, and the value of velocity over here will become equal to v is equal to x omega. So the velocity of this small patch at a distance x from the hinged point will become equal to x omega. So the small EMF induced in this element. So if I write the small EMF that is induced across the element of length dx, then by using the formula B L V, the length of this segment is dx and velocity is equal to x omega. So if I write the small EMF that is induced across the elemental length dx, then we can write an equation like this: B dx into x omega. And if I rearrange the term over here, we write it as B omega x dx. And if we integrate along the entire length of the conductor from 0 to L, then we get that the value of EMF induced will turn out to be B omega L square by 2. So the value of EMF that is generated across the end of a rotating rod, so we get an expression B omega L square by 2. And for finding an equivalent circuit, I can redraw this rotating disc in this fashion. So this rotating disc, this rotating rod can be drawn in this way, that this end will become a positive terminal and the outer terminal will become a negative end. So this will be behaving like a positive terminal and this will behave like a negative terminal, and the value of EMF is equal to B omega L square by 2, and it is rotating with omega. So this is end A, this is end B for the rod, and the value of EMF is equal to B omega L square. So again we can do the same way. The polarity is determined using right hand rule. So take your right hand in the direction of B, curl it in the direction of B. Your thumb is pointing towards the hinged end. So our thumb will be pointing towards the hinged end. So I can say that the hinged end will have a positive polarity and the other end will have a negative polarity. Or if we use Fleming's right hand rule, so if we use Fleming's right hand rule, then our index finger is pointing in the direction of magnetic field, that is into the plane of the screen. Our thumb in the direction of velocity, that is in the green direction. Then our middle finger is pointing towards the hinged end. So I will say that this end will be positive terminal and the other end will be the negative terminal. So the direction can be determined using the Fleming's right hand rule or by finding out the direction of V cross B. So both the aspects are possible, and over here we get the value of EMF induced due to the rotating conductor in a magnetic field, which is equal to B omega L square by 2. So we are dealing with a few numericals based on the concept which we have learned. So let us begin with the first one. A 5-meter long metallic rod is rotated with an angular frequency of 400 radian per second about an axis normal to the rod passing through its one end. The other end of the rod is in contact with the circular metallic ring. A constant and uniform magnetic field of 0.5 Tesla parallel to the axis exists everywhere. Calculate the EMF developed between the center and the ring. So if we are considering this problem, we are beginning like this, that the length of the rod is given to us as 1 meter, and it is rotating with a constant angular velocity, that is omega equals 400 radian per second. And the next thing is that the magnetic field of 0.5 Tesla is present in space. So if I apply the equation, E is equal to B omega L square by 2. So we can calculate it in this way, that 0.5 omega is 400 L square by 2. So over here we are calculating this to be coming equal to 100 volt. Let us deal with the next problem. The next one is stating a circular coil of radius 8 centimeter and 20 turns is rotated about its vertical diameter with an angular speed of 50 radian per second in a uniform horizontal magnetic field of magnitude 3 into 10 to the power minus 2 Tesla. Obtain the maximum and average EMF induced in the coil. If the coil forms a closed loop of resistance 10 ohm, calculate the maximum value of current in the coil. Calculate the average power loss due to Joule heating. Where does this power come from? So if we begin this particular problem, so it is stating that the radius is equal to 8 centimeter and the number of turns is equal to 20 rotated with 50 radian per second, and magnetic field is given to us as equal to 3 into 10 to the power minus 2 Tesla, and the resistance value is equal to 10 ohm. So the first thing that we are calculating over here is the area associated with each coil. So area is going to be pi r square, that is 8 by 100 square, and over here we calculate this value coming equal to 0.0201 meter square, and the number of turns that is associated over here is 20 turns. So I can write that the flux associated over here is equal to NBA. So we are writing it as equal to NBA. So if we calculate this value, we can write it as N is 20, B is 3 into 10 to the power minus 2 into area, that is 0.0201, and over here the value is turning out to be 1.20 into 10 to the power minus 2 Tesla meter square. So if we calculate the maximum induced EMF, so over here we can calculate the maximum induced EMF. So E maximum can be written as NBA omega, that is flux into omega. So if we multiply this expression with omega, that is 50, so we are obtaining a value that is turning out to be 0.603 volt. And if I talk about the average induced EMF, so over here it must be kept in mind that when the circular coil is rotating, so in one phase of the rotation, the EMF will be induced, if it's say in a clockwise sense, then in the other half, the EMF will be induced in the anti-clockwise sense, or I can say that the average value of induced EMF will turn out to be 0. So I can write that average induced EMF will turn out to be 0 because it is in clockwise sense in one phase and the another time it is in the anti-clockwise sense. So the average induced value is turning out to be 0. So if we are looking at the next aspect, that is the maximum value of current. So over here I can write that the maximum value of current I maximum is equal to E upon R, where E is equal to 0.603 upon resistance, that is 10, where it is turning out to be 0.0603 ampere. Now the next part of the problem is asking is the average power loss. So if we calculate the average power loss, so we can write it as EI by 2, and it is written as 0.603 into I, that is 0.0603 by 2. So the average power loss is turning out to be 0.018 watt. Now in this problem, it is also asking where does this power come from. So if we consider this, we say that the current induced produces a torque opposing the rotation of the coil, where the rotor is an external agent, and it must supply a torque to counter this torque in order to keep the coil rotating uniformly. So the dissipated power comes from the external rotor. So we are dealing with the next problem. So this time the problem is stating a jet plane is traveling towards the west at a speed of 1800 km per hour. What is the voltage difference developed between the ends of the wing having a span of 25 meter if the Earth's magnetic field at the location has a magnitude of 5 into 10 to the power minus 4 Tesla and dip angle 30 degree? So if we begin with this particular problem, the speed is given to us as 1800 km per hour. So the first thing that we need to do is convert it into meter per second, multiply it by 5 by 18, and we are attaining a value that is equal to 500 meter per second. The length of the airplane is given to us as 25 meter, and a magnetic field of 5 into 10 to the power minus 4 Tesla is present with a dip angle of 30 degree. So if dip angle is 30 degree, so over here I can calculate the two aspects of it. One will be the horizontal and the other will be the vertical component. So this will become b cos theta and the another one will become b sin theta. So, and it is the vertical component of magnetic field that is going to be responsible for the EMF induced between the tip of the plane. So we will be considering this value, that is BV is turning out to be 5 into 10 to the power minus 4 into sine 30, that is half. So we are writing it as 2.5 into 10 to the power minus 4 Tesla. And hence we can calculate the EMF as BLV. So B over here is equal to 2.5 into 10 to the power minus 4. The length is equal to 25 and V is equal to 500 meter per second. And on calculation we are turning out to be that it is equal to 3.125 volt. So this is the value of the EMF that is induced, or the voltage that is developed between the ends of the wings